so easy. I'm Linda Bastone. I'm the chair of Natural and Social Sciences. Some of you I know, some of you I don't. Welcome. This is our second talk this semester. We do 3 talks each semester, and this is a special one for us. This is our Sigma Psi lecture, and we have on the campus a Purchase College Sigma Psi chapter, you call it, and Sigma Psi is one of the oldest science honor societies in the country, so it's very exciting. Some of the officers are here with us today, Dr. Abrams, Lise Craddock, Lynn Winters, Joel, I don't know if you're affiliated, but many of our faculty are, and each year we have one Sigma Psi lecture where we invite one of the distinguished lecturers from Sigma Psi, and that's what we're going to do tonight. So you'll learn about that in a moment. I just want to first give a big shout out to one of our other sponsors, Con Edison. Con Ed has been a really wonderful supporter of our lecture series. Some of you know this because you see the logo on everything we send out in email and so on. But also I want to give a shout out to Laura Rizzo, who is here representing Con Edison tonight, today. And more importantly, I think, Laura is an alum of Purchase College, so it's very exciting that she is at Con Ed. And at Con Ed, I think I have this right, your title is Corporate Affairs Manager, is that correct? So we've been working with Laura, and she's been helping us maintain the support from Con Edison, which is really important to us, not only for the lecture series, but it also provides science experts to come into classrooms and laboratories to work with our students. And they've also supported student-faculty research, which if you're anywhere near senior year, you know just how important that kind of support is. And if you're not yet at senior year, you'll know when you do your senior thesis just how important it is to have some funding to enable you to do the high-quality research that you hope to and can do with your faculty members. So we're very grateful. Thank you so much. So tonight, we have Dr. Joel Tenenbaum here to introduce tonight's speaker. And Joel also has some titles I had to write down. And one of them is Professor Emeritus of Physics and Scientific Computing. And some of you may or may not be familiar with that term emeritus, but it's usually an honorary title that we give to faculty who have retired from a campus with distinction. So Joel did retire officially from the campus with distinction, but he also has another title, and it is Research Professor of Meteorology and Scientific Computing. And Joel actually got that title after having retired, because after he retired, he really just didn't slow down. So he's been continuing to do his own research, and also a little well-known fact for many of us, but maybe not for the students, he also consults on all of our weather-related decisions at the college. And if you heard his title, right, he's knows something about meteorology and scientific computing, so those things come in handy for the campus, and we're grateful for all he does for us. He'll introduce tonight's speaker, right? So give him a
I guess likewise I should be able to just stand up here. The scary thing on the meteorology is when you're all sleeping quietly during the winter, I'm sometimes up at 4 a.m. trying to decide what we should do about canceling or delaying classes. And I have nieces, nephews, and grandchildren who say, "You do what? Gee, can I have your job?" or something like that. It's my pleasure to introduce Dr. Tucker. We have a good deal of overlap in our existence. And I want to take a brief excursion on the background of NASA and the Goddard Space Flight Center, where Dr. Tucker is from, because it is really interesting and appropriate. Some of you, and I fear the students maybe much less so, may realize that only 11 days ago was the anniversary of the launch of the first Sputnik, the Russian satellite, which really revolutionized one's whole idea of rocketry in space. And it has a very interesting and direct history with Dr. Tucker's work, because that was October 4th, 1957. Both he and I were school children of various kinds, and it had a substantial effect on our own existence. Within 1 year, approximately, of that launch, NASA was created, roughly in 1958. And within 2 years, the Goddard Space Flight Center, where Dr. Tucker carries out his research, was also created. The Goddard Space Flight Center in suburban Maryland is the first of the multiple NASA centers. The significance, and this is related to Dr. Tucker's work, of Robert Goddard as a very underappreciated pioneer of rocketry. He came up with the idea both abstractly and concretely of, gee, maybe we can go out to space and go out to the moon using rockets, and the saga is far more complex. It's worth going in here. But one of the punchlines which came in an article by the New York Times was, maybe we can set off a burst like a flash bulb on the moon to prove we've gotten there. And the New York Times picked this up rather deprecatingly, and I will read you in detail from their editorial. Any journalism student here should take this as a cautionary tale. This is about 1920. After the rocket quits our air and really starts on its longer journey, its flight would be neither accelerated nor maintained by the explosion of charges it might have then left. To claim that it would be is to deny a fundamental law of dynamics, and only Dr. Einstein and his chosen dozen, so few and fit, a license to do that. Of course, Goddard only seems to lack the knowledge lashed out daily in high schools. Well, as most of us are aware, the Times was rather wrong, and the day after the Apollo 11 was launched to the moon, the Times said, July 17, 1969, further investigation and experimentation have confirmed the findings of Isaac Newton in the 17th century, and it is now definitely established that a rocket can function in a vacuum as well as in an atmosphere. The Times regrets the error. Various people at that point sensed that Earth observations might be in some sense as important, if not more important, than the actual lunar and planetary trips. And that brings us to some of the byproducts of rocketry and satellites and so on. The one we all routinely now make use of without thinking twice is GPS, namely, where your car is and sometimes where your parents want to track you down. But the relevance to Dr. Tucker's work is, as you will hear in some detail, that Earth observations are a very important part of what we do with satellites. Dr. Tucker started with both bachelor's, master's, and PhD at Colorado State University, primarily in the life sciences, but as he and I were talking before, he has a fairly strong background in mathematics. And a very small number of people here may still remember Dr. Paul Steineck, who was on the faculty, sadly died a number of years ago, who summarized that kind of dichotomy as, oh, geophysicists, they are geologists who can pass calculus. And Dr. Tucker is very much in that moray. Having done that, he eventually joined NASA and has used satellite data to study the Earth in research areas that include famine early warning, deforestation, desert boundary determination, ecologically coupled diseases, terrestrial primary production, glacier extent, and how the climate affects global vegetation. He has also led, very interestingly, groups in NASA's space archaeology program. He's authored or co-authored more than 180 journal articles, is a fellow of the American Geophysical Union and the AAAS, American Association for the Advancement of Science, and has been awarded several medals and honors, including NASA's Exceptional Scientific Achievement Medal. He'll speak to us today about the satellite, I guess it's up above me, the satellite record of the Earth's climate. Please join me in welcoming Dr. Compton Tucker.
Thank you very much, Joel. It's a pleasure to be here. So my talk, I'll spend maybe the first 35 or 40 minutes talking about the satellite record of climate, and then to purposely not leave people in a depressed frame of mind.
Can you speak louder or get the mic to a higher?
Would it be better just to speak like this? Or no? Okay, I'll hold the microphone. Is this better? If I start to deviate and you can't hear me, just say something. Yes, perfect. Okay, so in my presentation, the first 35 to 40 minutes will be a review of the satellite geophysical evidence for climate change, which I think is only people who are ignorant, stupid, or dishonest disagree with. And I'll explain why. It's simple geophysics. And that'll be followed by several things we can do right now to mitigate global warming, because it's very important to end on a positive note. We have a lot of work to do, and we need to work together collectively to achieve it. So this is my introductory slide, which shows weather, and weather through time is climate. Well, I have flunked.
Audiovisual.
Yes.
Manual, that's beautiful.
What command? This is forward, is it not? Okay. Thank you very much, Amanda. So this is just a slide of several of the Earth viewing satellites. As Joel mentioned, one of the byproducts of the space age is we have satellites which orbit the Earth. There are many of them which look down at the Earth, and there are many which look away from the Earth. And within NASA, about 40 to 45% of the NASA science activities involve Earth viewing satellites and Earth viewing studies, and the balance involve the study of the sun, astrophysics, and planetary science. So a very large part of NASA engineering and science involves building instruments, launching satellites to study the Earth, and then scientists like me who are at the end of the food chain who take the results and run off with them. So we're sort of like in a sports team, someone who scores the goal when there are many, many people on the team who contribute to everything up to that point. So this is one slide of the Earth which I took part in. I handled the photosynthesis on land in this image of the oceans and the land. And it's very interesting for several reasons, especially in the oceans. The blue areas in the ocean, like you see, if I can master this, change hands. So these blue, or these areas right here, which are dark blue, these are biological deserts in the ocean. There's no mixing of the water. There are no strong wind fields. There's no upwelling. And so there are no phytoplankton which are there. These are areas where in the 19th century you didn't want to be on a ship which was becalmed, because it would take you forever to get out of it, and it would be very, very, very boring to be stuck there. If you look on land, we have deserts like you see in the Sahara, here, also Arabia, this portion of Central Asia. And then where you see on land these dark, or these green colors, these are where we have a very large density of chlorophyll plants. And you can, of course, note this is the tropical forest, the Amazon, the Congo, so on and so forth. And of course, we're in a very forested area of the northeastern United States. So these are some of the uses which you can use satellite data for, or to make beautiful visuals like this. If you want to see this in a visualization sense, go on YouTube and look for NASA Living Planet. It's been viewed almost 2 million times, and it shows these data in a time series, and it's quite big, it's quite spectacular. Now, there are more than 1 trillion galaxies, and we know this from the Hubble Space Telescope, but there's only one planet we know which has life, and that is the Earth. I would think this would make people very conservative about how they treat the Earth, and indeed they should. Now, as Joel mentioned, one of the major contributions of NASA was what NASA has provided about the Earth. And this picture from Apollo 8 taken in December of 1968, looking back at the Earth, is iconic because it shows the Earth, this blue dot in space, completely surrounded by the vastness of space, and it conveys to all of us that the Earth is very unusual, very unique, and that's where we are, and so we better take care of it. Now, before I go further, it's important in science and in logic and everything to have definitions. And without proper definitions, logical discourse is impossible. And without logical discourse, nothing can be accomplished. This is not something new, this is from Confucius. So in geophysics, things are specified what you're measuring by the laws of physics, and I'll be showing several examples of those in my talk. So I'll be talking about the satellite record of climate, and sea level is the unequivocal indicator of climate, whether the Earth is warming or the Earth is cooling. At the same time, it's important to look at the sun, and there is no change in the sun. And I will show that. And then I will also show that ocean temperatures, surface temperatures, atmospheric temperatures are all increasing. And also the glaciers and Arctic sea ice are receding or melting. Now, one of the first things we need to look at is the sun, because some people say, oh, the Earth is warming, but it's just because of natural cycles. Well, that can only come from variations in the total solar irradiance of the sun through time. And since 1978, we have had satellites in orbit which study the sun. But if you look at these data, you'll notice here are 3 different satellites. This is the Earth Radiation Budget, this is ACRIM, and here is a total solar irradiance instrument on NOAA 9 and NOAA 10. They're all looking at the sun at the same time. They should be measuring the same geophysical phenomena in terms of watts per meter squared, but they're slightly off by only a few watts per meter squared. Here's the scale over here. So this is 1375, here's 1365. So we're only talking about a few watts per meter squared, and this is due to how these instruments were calibrated. If we look further, over in 2005 or so, here's an instrument, here are some instruments here. They should also be measuring the same thing because they're looking at the sun, they're measuring total solar irradiance. So a group of heliophysicists, people who study the sun, who are physicists, got together and they have intercalibrated all of the total solar irradiance data. And when they have done that, they bring everything into compliance. And this was done by using the more recent data right here from the total irradiance monitor, which is presently operating in space. This involved people from the Bureau of Standards as well as many national and international people who study the sun. So now we have a very good idea of what the sun is doing. Let's extend these data to 2010. Let's extend them now to through 2018. And one of the features of the sun during the satellite records is it is remarkably consistent and non-varying. The sun is not more energetic in warming the Earth, it's constant. And many people make the argument that civilization could not have arisen if the sun was variable because it would have crashed many civilizations. Now that is an anthropological argument. I will restrict myself to just talking about what we know since 1978 through the present in terms of the energy output of the sun. And that's represented here. And so we see a variation of 1 part in 500, and this translates to a very, very small temperature increase, which is associated with the 11-year solar sunspot cycle. Now, I will digress into history. This is Pearl Harbor on December the 7th, 1941. And in the case of Pearl Harbor, geophysical observations were ignored by people who could have prevented this from happening. What happened on the north shore of Oahu on December the 7th, there was an operating radar station by this gentleman and one other Army corporal or private. They called up this guy at Hickam Field, and reported a huge number of planes coming in from the north towards Pearl Harbor. This guy said, I don't believe you, I don't know what you're looking at, stop doing what you're doing and come back to Pearl Harbor. They continued to operate their set and observe the planes, and this is what resulted because of that. Now, in the Battle of Britain, radar over a year earlier was fundamental to the British defeating the German Luftwaffe. They had a much smaller force, but they used radar to detect when the Germans were coming and where they were, so a smaller force could be deployed to defeat a larger force. There is no excuse why this didn't happen at Pearl Harbor. Now I'll turn my attention to sea level, because sea level is measured by radars on satellites. And so here's an example of sea level. And what they observed is a sea level rise on the order of 3 to 4 centimeters per decade, or 0.3 to 0.4 centimeters per year over this time period. So here are what the data look like through February of 2019, and you see this continuing here. So now we're right up in here, and of the sea level rise, half of it is due to the melting of the ice sheets of Greenland and Antarctica, and half of it is due to water getting warmer and expanding. I will show subsequently how we measure this with satellites for the melting portion of the ice sheets, but how do you think we're able to use satellites to measure the temperature of the oceans? We can't. But many of our oceanographer friends have a very ingenious method of doing this. I draw your attention to the lower right-hand corner here. On the 12th of October, just 3 days ago, there were 3,865 of these autonomous drifting buoys in operation. And here's where they were in the world's oceans. Now these buoys are very ingenious. They're thrown off of ships, as this woman oceanographer is doing here. They then descend to 1,000-meter depth over about 6 hours. They then drift for about 9 days. They then descend to 2,000-meter depth, and they float there for a day, and then they gradually surface, and all the time they are measuring salinity of the ocean and its temperature and storing it. When they surface, they have a direct burst broadcast to a geostationary satellite. Those data come down to the Argo headquarters. This is called the Argo program, and it's from those data that we have ocean temperatures with depth. It's very ingenious, it's unequivocal, and it's widespread and involved many countries. And you can see there are almost 4,000 of these in operation at any given time. Now there's another satellite that you probably haven't heard of. It's called GRACE. And GRACE is an acronym for Gravity, Recovery, and Climate Experiment. And this is a satellite which measures the gravity field. And it does so very, very precisely. You never hear the climate change deniers talking about the GRACE theory, and I'll explain why. So these are in orbit about 500 kilometers above the Earth. They're separated by about just over 200 kilometer distance. And they can measure by radars on these two satellites. Here's one satellite, there's the other. And they can determine the accuracy between the satellites to a fraction of a human hair, to 1/100th of the fraction of a human hair, or 0.001 millimeter. And then by using Newton's gravitational formula, which is here, they can determine how the mass on the surface of the Earth is varying. So what they can do is they're orbiting the Earth. What they are reading out, the data they're reading out, is how these two satellites are separated. So for example, we'll say there's someone in the front seat sitting where I was earlier. The satellite goes over, and if they have gained weight, then the first satellite will speed up because there's a stronger gravitational attraction. And then the second one will speed up as it comes over. If that mass is lost, that will not happen. So by analyzing the variations in the distance between the satellites and knowing their orbits precisely, mass can be calculated directly in units of mass. And that's what's done. So there's an example here of an ice sheet. in June of 2002, June of 2005. And because there's more mass here, this would accelerate the satellites respectively, and that would not occur here to the same degree. So here's how the two satellites are. They are separated by about 220 kilometers, and all they record is the continual distance between them to this accuracy. What do some of the data look like? These data have revolutionized our understanding of the ice sheets. So here's Greenland. So what do we see from the gray satellite? Starting in 2002, we see this loss in the summer, an increase in the winter, loss in the summer, so on and so forth, like this. Now, this figure only goes through 2016. I could have extended it through the present, but I really like the graphic associated with it because it shows during this time period where mass was lost. It was lost in these areas in Greenland, and we read out the mass in units of mass because we understand gravity. Let's look at Antarctica. This shows similar things in Antarctica. This loss from West Antarctica. And here is the loss with the seasons also up through August of 2016. So it's satellites like the GRACE satellites and now the GRACE follow-on mission, which are used to understand how the mass variation of the ice sheets is varying with time. And from that you can calculate what the sea level rise from the melting of the ice sheets is, and from Argo what the thermal expansion is. Now, you never hear the climate change deniers arguing against the GRACE data or using gravity as a geophysical variable. Why is that? Simply because you can't fire a missile from point A to point B on the Earth's surface and be assured of where it will land if you don't know the gravity field. It's very simple. So anytime I talk to someone who says, I don't believe this bunch of BS, what you're talking about, I say, well, what about the gravity field? Do you believe it? How do you account for it? They will never respond. Now, a cautionary tale about Greenland and also Antarctica. In Greenland, these blue portions of Greenland are below sea level. All of these areas are slightly above sea level. So one of the problems in terms of if you're talking about ice sheet collapse, you need to be worried about areas which are below sea level because warmer water could come and melt a lot of ice. Now, this is especially true in West Antarctica. This shows Antarctica going from here across from East Antarctica to West Antarctica, from B to A, or A to B. And so this is the underlying Antarctic topography. In this portion of East Antarctica, it's all above sea level, but in West Antarctica, it is not. And this is a transect going from this to here, across here, and this is what it looks like. Here's the underlying topography, and so this portion of the West Antarctic ice sheet is largely exposed to melting from warmer oceanic waters. Now, one of the things about ice, and it's important to also take into account poems and things of a literary nature when you're studying science. This is a poem I like. It's about ice. Ice asks no questions, presents no arguments, reads no newspapers, listens to no debates. It is not burdened by ideology and carries no political baggage. As it changes from solid to liquid, it just melts. And that's from Henry Pollack and his book, World Without Ice. This is exactly what happens. Ice on the planet is very close to the melting point, and we have to worry about a warmer climate, it will melt more ice. This is especially true of the ice sheets, first in Antarctica, and then secondly, Greenland. Now, we're able to measure sea ice unequivocally in a geophysical sense because there's a fundamental difference in the spectral emissivity of sea ice in ocean water. And so it's like looking in a dark room with a flashlight, and you see the flashlight when it comes on. And so sea ice has a spectral emissivity at the wavelength of 1.5 centimeters of about 0.8 to 1, whereas the spectral emissivity of seawater is on the order of 0.4. This makes it, in a geophysical sense, trivial to measure very, very accurately. So this is what the Arctic sea ice variation looks like. In January, in all Januaries from 1979 to 2019, it comes down like this. But let's look at the sea ice minimum for Arctic sea ice, which occurs in August. So you have these same trends by month for all years, but this is most pronounced because most of the melt has occurred by August, and this represents the minimum. So it's coming down like this, and so this is due to some variations in the Earth's climate, but the trend is unequivocal and is this ice loss with time because of warmer temperatures. Now, if you look at Antarctica, you see something very different. You see no variation in the sea ice of Antarctica. So this is frequently used by the climate change deniers. You say, if you look at the Arctic and the Antarctic, we see trends in the Arctic, but we don't see trends in the Antarctic. What's going on? And they use this to cast doubt upon people who say the Earth is warming. Here's a figure from Jim Hansen, formerly of NASA at the Goddard Institute for Space Studies, showing the same thing. Here's the Arctic, here's the Antarctic. So, if we look at the Arctic Ocean, it's a simple situation. The Arctic is an ocean surrounded by continents. So the water exchange is much, much lower than it is for the Antarctic, which is a continent surrounded by oceans. So it's impossible to have a thermal feedback in Antarctica because all the heat is dissipated into the Southern Ocean. Now the Earth is also very fortunate, we're also fortunate, because we're here because of this, is we have a magnetic field. This deflects the solar wind, as you see in this cartoon, and this is very important because the solar wind can strip off the lighter elements of an atmosphere, a planetary atmosphere. And indeed, this is what has happened to Mars. There's a mission called MAVEN, which has been studying the atmosphere of Mars, and they report that the solar wind has been stripping off the lighter elements of the Martian atmosphere to its present state. And so this is very fortunate. Now, this is what the atmosphere of the Earth looks like if you're in orbit, in the International Space Station, or in the space shuttle. It's this thin film that you see like this. You see the sun rising. Now, it's very easy to do a simple calculation. I'll be happy to send anyone who's interested in this the spreadsheet on it. You simply calculate the energy from the photosphere of the sun. You propagate that to Venus, the Earth, and Mars. We know from our astronomer friends what portion of that energy is absorbed. From that, you can calculate what the temperature of Venus, the Earth, and Mars should be without an atmosphere. So I'll jump to the chase. When you do this, without an atmosphere, the temperature of Venus should be 64 degrees Fahrenheit, the Earth should be 1 degree, and Mars should be about minus 89 degrees Fahrenheit. Now we know this isn't the case, and it's because we have an atmosphere, and the atmosphere is an insulating blanket for the Earth, if you want to think of it that way. So the actual temperature of Venus is on the order of 800 or more degrees Fahrenheit. The average temperature of the Earth is about 62 degrees, and on Mars it's very similar, it's 81 degrees. So this is why the composition of the atmosphere in terms of trace gases, especially carbon dioxide, is very, very important. Now, in 1900, this chemist and physicist, Svante Arrhenius, a Swedish professor, proposed that the combustion of fossil fuels, from the combustion of fossil fuels, carbon dioxide would accumulate in the atmosphere around 1900. And in 1958, this fellow, Dave Keeling, who I had the privilege of publishing 3 or 4 papers with, started making measurements on the Mauna Loa volcano on the island of Hawaii to study the carbon dioxide concentration in the atmosphere. This curve is iconic, and it is called the Keeling Curve after Dave Keeling. Now, Dave told me that when he started making these measurements, they go up and they go down. And so they reach a minimum when plants in the northern hemisphere are photosynthesizing and sucking carbon dioxide out of the atmosphere. The increase that you see over time, this is due to the buildup of carbon dioxide in the atmosphere from the combustion of fossil fuels. So when Dave Keeling started making these measurements, they increased to a local maxima in probably April or May, before the growing season starts in the northern hemisphere, and then they decrease to a minimum, which occurs in September. Dave Keeling thought he was making a mistake. Dave Keeling was an excellent chemist. He was the most compulsive person I've ever worked with. He would fight tooth and nail to be the second or third author on a paper instead of being the third or fourth author. And he was great to work with unless you had arguments about the order of authors. And so by his perseverance and excellent chemistry is why we have this curve. And so right now, as of a few days ago, the atmospheric carbon dioxide concentration is almost 409 parts per million. So we're right here, and we're just about to start the increase to, as fossil fuels will increase in the atmosphere during the winter. Here are these data going from 1700 through now. Here's the Keeling Curve. Here are data which have been formed by studying ice cores. Now, that's what's going on in the atmosphere. Carbon dioxide is increasing, and carbon dioxide absorbs outgoing long-wave radiation from the Earth. Let's look at surface temperatures. Well, there are several groups. There are 6 groups that use the same data with different interpolations and different reference years to measure surface temperature. So these are all based upon local weather stations which report data. They have to screen them, things like that. And so if we look at these data, they are extremely similar. The satellite record starts here. All of these data are based upon surface observations, and they are now in complete agreement. Now, curiously, the Berkeley Earth study was originally funded by the Koch brothers. And they were very skeptical about what Jim Hansen and other people were doing. But now they all realize that the sun rises in the east and sets in the west, and the same is true about the surface temperature data. Now, it's different when you go to satellite data, which can measure the temperature in the upper atmosphere and lower atmosphere. And there you see something which is very curious. You see in the stratosphere that things are cooling, but in the lower troposphere, you have an increase in temperature. Well, this is completely consistent with global warming because the absorption of outgoing long-wave radiation occurs in the lower atmosphere here, and so there's less of the outgoing long-wave radiation to reach the stratosphere, so it cools. So rather than this being proof against global warming, this buttresses global warming. So now we come to the global biosphere. This is something which I was really happy to be part of, and I've used this on Christmas cards. And I get into arguments with my oceanographer friends over whether the land is more important or the oceans are more important. And I ultimately have to say, well, I think we all live on land, so I think you're being a traitor to all of us on the land. Anyway, we also know that our planet supports an amazing biological diversity. These are 2 of my favorite zebras. Here is a pod of whales. Here is a very charismatic man in Florida, and he's saying thanks to Earth's magnetic field and plate tectonics, which are really important for our climate system. So now we come, what the hell do we do? Do we get depressed and do nothing? Of course not. There are many things we can do and are doing, and we need to continue doing them and doing them in a more concentrated manner because we want to leave the Earth in a better condition than it is now. So one of the things right now that's happened is that the price of solar, which is right here, the price of wind in terms of the energy produced per kilowatt has fallen to somewhere in the order of about between $45 and $50. The price of coal is twice that, $100. So the reason coal is not doing well is because it's expensive, it's getting more expensive with time, and there are all sorts of secondary problems associated with it, like a lot of carbon dioxide which results from the combustion of coal, because it takes two phase changes, from a solid to a liquid to a gas. If we look at methane by comparison, which is natural gas, which is right here, natural gas is a perfect complement to renewable energies from wind and from solar because it can come online in a matter of 20 or 30 minutes, whereas a coal-fired power plant takes 8 or 10 hours to spin. So natural gas is a perfect short-term complement to renewable energy. Now there's something called the localized cost of energy, and that's what the acronym LCOE means. And this shows more or less the same thing. So what's happening is the price of solar is falling, and it tends to obey Moore's law, where the cost falls by half every 2 years or so. So here is solar, here's wind, here's coal. So the reason coal is being beaten up and is falling out of favor is for simple economics. And if you use an economic basis for deciding what you use for power plants, coal will lose every time. So what can we do? There are several myths. We hear people say wind and solar are far too expensive. Nonsense. If you look at what I just showed you and many other examples, economists say it's just the opposite. They're so inexpensive we can't avoid not using them unless you want to spend money unnecessarily. Another myth, wind farms are a scam. They're not green and actually use more electricity than they produce. Not true. And then the third myth, we would die without coal. We will die with coal. I'm exaggerating, but of course the sun doesn't shine or the wind sometimes stops blowing. In those cases, natural gas is a much better complement for renewable energy. Now there's a lot of work being done in carbon capture and sequestration, taking carbon out of the atmosphere. There are many, many people spending billions of dollars to perfect this and bring it online. Now it's probably going to take a lot of energy, but that energy could come from renewables like solar and also wind power. So the idea here is you take carbon dioxide from the atmosphere and then you turn it into something solid and store it, or you bury it in caverns underground. So what can we do? So here's a picture. In fact, the next car I get is probably going to be a Chevrolet Bolt, which is here. Here we have solar. Here we have bicycles. I'm a big bicyclist. And I've never heard any of our politicians say, why don't we have tariffs on imports to our country based on the carbon emissions of those countries? It seems logical. If people are going to use coal to power whatever they're producing and trying to sell it in the US, we should be able to say no, because we have the technical means to measure carbon emissions from satellites. What have we done? Well, I point to the Manhattan Project, which started in 1942, and by 1945, here is Dr. Oppenheimer, who was in charge of it, and some of the physicists. This is a good example of a focused activity where you want to get something done, and it was crucially important. Also, the Apollo program was President Kennedy on the 12th of September 1962 at Rice University when he said, we will go to the moon and do so within this decade. That only took 7 years to do. And here's a picture from Apollo 11 taken with a good view of the Earth. So we can do things like this. We've done them in the past, but we have to put our energy to them. We have to do them in a systematic way and simply be successful, because life as we know it on this planet depends on it. Now we know what happened at Pearl Harbor because geophysical variables were ignored. So here's the same fellow who said no, there are no planes coming in. Here's an actual photograph of the oscilloscope. These are the Japanese planes headed in. Here are the Japanese planes. Here's the radar antenna. We know the penalties for ignoring geophysical variables are severe, and we want to avoid that. We're in a similar situation now. When I look at the geophysics of climate change, it's overwhelming. I've avoided a lot of areas. I'm trying to be positive in what we can do about it, and I'm not a gloom and doom person. I'm not a gloom and doom person, and neither should you be. So thank you for your attention. And then I'm from NASA, and one of the cool things about NASA is we organize around projects. So we have people who are in charge of visualizations, of the presentation of what we do. We have engineers, we have scientists, we have program managers, people who are specialists in accounting, who make sure that the funds are spent when they need to be spent on what needs to be done. And so this is one of the cool things. So I've worked for NASA now for 42 years, and it's still a lot of fun. I'm by far the oldest person in my group by a factor of 2 or more, but it's great working with young people, and many of you have great skills, and keep perfecting them and put them to use. So thank you for your attention. I'll leave a PDF file of my presentation if anyone would like to look at it. I only ask that if you find any mistakes in it, please email me and point me out the mistakes. Thanks for your attention.